So in today's video, we're actually going to be finding the derivative of e to the x and a to the x for some constant a. Well, it's actually quite simple, really. Well, the derivative of e to the x is simply just e to the x. And then for the derivative of a to the x is just a to the x multiplied by ln of a. There we go. We got a video. Sweet. Alright. That was that might have been too short of a video, otherwise you would have looked at the time below. So in all seriousness, we're actually going to be proving the derivatives for these two functions by definition, obviously. So yeah, it wouldn't be a video if it wasn't 10 minutes. It's simply just listing out the answers. So these two functions are basically pretty much just elementary derivatives to natural logarithm functions in particular, and exponential functions. So first thing we're going to prove is the derivative of e to the x is equal to e to the x itself. So let's get started. So let's first recall that the derivative for the definition of derivative is simply defined as f of prime of x equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, so now we can just plug in our x plus h into our input for our function e of x. So this is simply just the limit as h approaches 0 of e to the x plus h minus e to the x divided by h. And then we can actually, using our log rules, we can actually separate it out with the same base. So this will be the same as limit as h approaches 0 of e to the x multiplied by e to the h minus e to the x divided by h. And then we can factor out the e to the x, raised to e to the x, so it's just e to the x, let me fix my where I positioned that. E to the x multiplied by e to the h minus 1 divided by h. And notice that because e to the x, it does not depend on h, simply meaning we can actually move this outside of the limits. So same as e to the x multiplied by limit as h approaches 0 of e to the h minus 1 divided by h. So this is what we have so far. Now, if you recall from the last video I did with the natural logs, we're actually going to be doing a little similar method by using substitution. So what I'm going to do is I'm going to let's define y equals the numerator e to the h minus 1. Okay, so, and also pay attention that as h approaches 0, then if you plug 0 into here, e to the 0 is 1 minus 1, 0. Then that means y approaches 0. So in other words, the limit, well, if we just pay attention to y itself, if we were to take the limit as h approaches 0 of y, it's just 0. So that would be important when we do the substitution. And also, let's also fix this a bit such that because we have an h, so let's just so we want this by itself and then substitute it from there. So we can add the 1 to both sides. So this will be y plus 1 equals e to the h. And then we can take the natural log for both sides. So we have the natural log of y plus 1 equals h. All right. Now with that, now let's actually plug in our substitutions. I'm not going to write e to the x when I'm doing the substitution. I'm just going to focus on just this limit right here for now. We'll clean out everything later in just a bit. So I think I'm going to write right over here. So now we have, so this time, because now we're having everything in terms of y. So that means when we set h approaches 0, so y also approaches 0. So we're going to have everything with the limit approaches y of 0. And so e to the h minus 1, we set that as y, and then divided by h, which we have is ln of y plus 1. Okay? Now what we can do is we can actually divide the y from both the numerator and the denominator. So simply we would have the limit as y approaches 0 of 1 divided by, I'm going to write this as 1 over y multiplied by the natural log of y plus 1. And using natural log rules, we can add this, the y 1 over y is in front of the natural log, so it treats it as an exponent. It treats it as an exponent to y plus 1 when you're using natural log rules. So write this as the limit as h approaches 0, or not h, y, excuse me. The limit as y approaches 0 of 1 divided by the natural log of y plus 1 of 1 over y. And an important thing to observe is that ignoring the natural log, we have y plus 1 raised to the 1 over y. So what that means is that it's also defined as Euler's constant. And I'm going to write Euler's constant. This is in terms of limits. It's defined as e equals to the limit as y approaches 0, could be any variable you want it to be, as long as it's in this format, 1 plus y raised to the 1 over y. So simply, when you distribute the 1 over y into y plus 1, this is the same thing as e. It's equal to e. So this is the same as 1 over, the limit as y approaches 0 of 1 over ln of y plus 1 raised to the 1 over y, which is e, also known as ln of e, which is equal to 1. Now, this is just 1, but when you take the limit as y approaches 0, it's simply just 1. So now going back to here, we have that, where am I at? Okay, we have that e to the x limit as h approaches 0 of e to the h minus 1 divided by h. And we said that e to the h minus 1 over h, this is actually equal to 1, so it's e to the x times 1, and it's simply e to the x. And that is our derivative for e to the x. The derivative of e to the x is equal to e to the x. Pretty simple, right? It's the same thing as, the same method as trying to derive the natural log, which is equal to 1 over x. Same method. Okay, so moving on, we're going to be moving into the next function, a. For some real number a, the derivative of a to the x is equal, let me write it down first, a to the x is equal to a to the x, not finished yet, a to the x multiplied by ln of a. Okay. So let's start proving this. Let me rewrite the definition of the derivative of function. So f of x plus h minus f of x divided by h. So now we just plug in x plus h as our input for our function a to the x. So that's simply limit as h approaches 0 of a to the x plus h minus a to the x divided by h. Pretty similar to e to the x. Actually, it's doing the same methods again. So using our rules of natural logs, we can actually split the base into 2. So it's being multiply a to the x times a to the h minus a to the x divided by h. Factor out the a to the x. So 0 of a to the x times a to the h minus 1 divided by h. Okay, and just like before, a of x, it doesn't depend on h, so we can move the a to the x raised to the x outside the limit, and we'll just be focusing on the limit in this case. The same thing as before when we just showed the derivative for e to the x. A to the h minus 1 over h. Okay. So this is very, very similar to what we had before. Instead of e, so we have some real number a. We're going to be doing, again, it's the same. The next step is the same thing. We're going to be doing a substitution. Instead, last time what I did for the e to the x, proving it's finding the limit for this. I only did the substitution for the numerator. Instead, I'm gonna do the substitution for the whole function inside a to the h minus 1 divided by h. So let's do that. I'm gonna let y equals, let me say, let y equals the whole function a to the h minus 1 divided by h. Okay, now let's actually multiply the h to both sides. So this will be h times y equals a to the h minus 1. Add the 1 to both sides, so h to the y plus 1 equals a to the h. And then take the natural log of both sides. So this will be natural log of hy plus 1 equals natural log of a to the h. The h goes down to the front. So y plus 1, or hy, whoops, plus 1. And then the h comes out in the front. And then divide h by both sides to get, or here, I'm gonna write this here, right over here. ln of a is equal to ln of hy plus 1 divided by h. I'm gonna box this for now because this is gonna be important for later. So let me just box this. Blue. Okay. Also, one thing to note is we should also say that as where am I at? Okay, as h approaches 0 for this, then actually and then h times y also approaches 0 as well. As h approaches 0 here, a to the 0 is 0. So this would have to mean that the hy also has to be 0 as well. Right here. I pointed the wrong way. Right here. As h approaches 0, so a to the 0 is 1 minus 1 0. Then hy has to approach 0 as well. So this is important to say when we do the substitution. Okay. So. Now, when we rewrite the substitution, this is the same thing as writing ln of a is equal to the limit as, or let me not, well, actually, first, let's first actually manipulate this equation a little bit, the right side of the equation. So, I'm actually going to multiply both a y multiply a y to both the numerator and the denominator, and it still will equal the same thing. So when we multiply the y to top and bottom, so we would have, write the y first, not the ln. So we would have y ln of hy plus 1 divided by h to the y, okay? And this is still equal to ln of a, don't forget that. So we take the limit, or when we take, let me write the limit first. And we're taking this, since we're doing the substitution with, when we have h approaches 0, then substitute for hy approaches 0. So the limit as hy approaches 0 of y ln of hy plus 1 divided by hy, okay? And y doesn't depend on hy, so that means we can move the y to outside. So y, the limit as hy divided by 0 of 1 over hy ln of hy plus 1. This is very interesting because this is actually very similar with the same method with using Euler's constant. And I'll reiterate again one more time. Euler's constant is defined as the limit as y is approached 0 of 1 plus y divided by 1 over y. And then this is in terms of hy, so in this case we have the limit as hy approaches 0 of natural log of 1 plus, so simply, it's just y times the limit as hy approaches 0 of, this is ln of e, which is equal 1. So the limit as hy approaches 0 of 1 is just 1, so it's y times 1 equals y. And this is interesting because y, this would have to mean y is equal to ln of a, where we also said, when we also defined y is equal to a to the h minus 1 divided by h. Right, oopsies. Here, I'm gonna rewrite it this way to reiterate. So we said y is equal to a to the h minus 1 divided by h, and we said that y has to equal ln of a. Y is equal to this whole thing here, which is equal to ln of a, and therefore y has to equal ln of a. I've said that so many times. So, backtrack to here. That means a to the x times the limit as h approaches 0 of a to the h minus 1 divided by h. We said that this is ln of, we said that this limit here is ln of a, so it's a to the x times ln of a simply equal a to the x ln of a. And that's why I boxed this, because this would be important for later. This is exactly why. Alright, cool. Looks like I'm done. I like to, probably in my next video, I like to try proving the derivatives by definition of all the trig functions, simply with, you know, sine, cosine, tangent, cotangent, secant, cosecant, those 6 trig functions. So just be on the lookout for that. Hopefully that'll come out soon. I know I've been on hiatus for like a month just because things were just happening with what's going on, you know. I just rather not talk about it. So yeah, thank you guys for watching. Like, comment, and subscribe for more. Check out the last video I did, which was proving the derivative by definition of ln of x, which is equal to 1 over x. Very similar method to just what we did with a to the x and e to the x. They're very proof by definition. They're similar methods. So yeah, see ya.